So looking at the pH of solutions, so what I want to do is I want to go through the solutions that you measure the pHs of last week or week before. Can somebody remind me what the solutions, do you have your data from there? What solutions you had measured the pH of? For the lab. For water? Oh, I mean, it was for that lab where we had all the solutions in the hoods, and then you were measuring the pHs of those. So, somebody give me any of the solutions that you have data for. We'll take a look at those. I think like there's a mix of salts and acids. All right, sodium carbonate. And the pH you got was 11.10. All right. Anybody else get a pH for this? What did you get? 10.92. Okay. Anybody else? Dan? 10.87. Okay. 11.49. Okay. Other data? No? How about from this side? All right.
Ours might be a little off, but it was
9.5? Okay. All right, so what we're going to do is, for us, we don't know which one is the correct value. Maybe 9.5 was the correct value. Who knows? Chances are, though, maybe not, because the other values are higher. So what we're going to do is, since we don't know what the true value is, what do you normally do if you have a number of runs? Well, normally what we do is we take a number of trials and then we get the average of the trials. And so that's what we're going to do here. We're going to take the average of the data here. And so with Excel, we can take the average pretty easily. There are a whole bunch of built-in functions. So I'll just take the average here of this data. And then I see my average is 10.776 here. So that's probably the best number that we'll have for this. Now, when we take an average, we'd like to get an idea of how broad the spread. That 10.776 could have come from data like this. This is hypothetical data, but let's say I had 10.775 and then 10.776 and then a 10.777, something like this. And then let's see what the average here looks like. So I'm just going to copy and then paste that there. And I get the average, the same average. Excel, you can change the number of sig figs here by increasing or decreasing it. But do you see, I see the same average here, basically. But what's the difference? The difference is in the spread. Do you see this one has a very wide spread of data, all the way from 9.5 to 11.1? Whereas this one has a very tight spread of data from 0.775 to 0.777. And so the thing is, when we look at the average, can you tell how wide the spread is of the individual data points? There's no way you can tell, so we lose that information. But we don't want to lose the information, because an average is what we call data reduction. So we're taking all this data and reducing it to the average. But in that process, we're losing the spread information. And therefore, in science, we don't want to lose it. And so what we do is we have something called the standard deviation. The standard deviation says, okay, if you were to graph it as like a histogram, the data, in fact, we could probably graph this as a histogram. Let me just do that here by inserting a chart. And I'm going to go with a histogram chart here. Actually, I need to make these smaller, minor grid lines. Bin width 0.1. If we were to take if we were to take a large amount of data, we'd generate probably a histogram that looks like a bell-shaped curve, where most of them are going to be around the true value, and then there's going to be some outliers on both sides. And this just randomly happens, And so what we model this is we model this with a bell-shaped curve, thinking that, random error occurs randomly. Some are below, some are above, and we expect that. And so with a bell-shaped curve, we have something called the standard deviation. A standard deviation, we can fit like 67% of the data within plus or minus one standard deviation of that. And so it's going to look something like this. Actually, this doesn't have enough data. I'd have to collect a lot of data here, which I could. But basically, if we take a large number of data points, then we're going to get, the most around the true value, and then we'll get some above the true value and some below. This is eliminating systematic error. So if we have no systematic error and we take an infinite number of data points like this, then what we're going to get is a distribution of measurements that looks like this. And so statistically what happens is that we're going to get some that are going to read too high, and then we're going to get some that read too low. And then we can average that out if we had an infinite number of data. But we don't have an infinite number of data. This looks nothing like this here. If we had an infinite number of data, then we can see where most of the data points lie, and then that should be closer to the true average. But what we're going to do is we're going to do some statistics, and we're going to try to model this here and see, how wide this is. And then what we're going to do is we're going to try to capture it within one standard deviation. If we look within one standard deviation here, it should capture like 67 or so % of the data here, something like that, within plus or minus one standard deviation. That means there's like a 33% chance it's outside of one standard deviation here. So what we do is we try to model this like this, but it's not. We don't know where the true value lies. So what we're going to do is we're going to come up with this curve here that's going to say that the average, the true value, is going to lie within some kind of distribution. Let's see, some sort of distribution. The tighter it is, let's say I only had these 3 data points here. If I only had these 3 data points, then I can model this with a much tighter curve like that. But since I have these 2 data points that kind of outlie, then it's going to be a much wider curve like this. And so what we have is we have a difference in what we call confidence interval. So for example, if the data are like very tight, like we see here, we're going to have a different level of confidence. So this is a very tight set of data here. Let's go ahead and plot this one out. So I'm going to just insert a histogram. I didn't want to format. Going to make it probably a little. Let's big. So here, let me scale this a little bit. Well, I'll have to scale this down. So here we're going to have just a much tighter distribution. Get the bars about the same size. And so here we're going to have a bit more confidence in the average, whereas here we have a much wider distribution, so we have a little bit less confidence in the average. And so what we do for this is we'll just model it, and then we're going to determine the standard deviation. So Excel will do this for us. It's just a built-in function. So we'll just say STDEV for standard deviation. And we have three types of standard deviations in Excel. If I look at standard deviation.p, it says calculate standard deviation based on the entire population given as arguments, ignores logical values in text. Then we have standard deviation S, estimates standard deviation based on a sample, ignores. And then we had standard deviation A, based on a sample including logical values in text, and standard deviation PA, and then standard deviation just regular, but this function's no longer compatible. And those are the standard deviations. So what we have is we have a limited sample, and so we pick standard deviation.s here, like this, and then I'm going to use this function here, and I'm going to just take the standard deviation of our data here, right here, and then close that. All right, and that gives us our standard deviation. Now take a look at the two standard deviations. Do you see that this standard deviation here is quite huge? It's 0.75, whereas this standard deviation is quite small, which means that what we read as the standard deviation is that there's like a 67% chance that the true value lies within plus or minus this range. So it's the average plus or minus this range. But in science, plus or minus one standard deviation is not enough, because there's still a 33% chance it lies outside. So what we're going to do is we're going to minimize the chance it lies. We only want a 5% chance it lies outside. And so what we're going to do is, rather than taking a standard deviation, which is what we call the 67% confidence interval, this would be the 67, I think, I forgot, 67% confidence interval. So we have 67% confidence that it lies within such range. But what we want to do is we want to widen it out a little bit, and what we want to generate is something called the 95% confidence interval. The 95% confidence interval is about 2 standard deviations. So if we go plus or minus 2 standard deviations, then that captures 95% of this plot here, and therefore there's only 5% chance that the average, and it's a little weird, but the average lies outside this here. So the 95% confidence interval is common. That in Excel, it's a built-in function called confidence. So if we look at confidence, there's confidence.norm, returns the confidence interval for a population mean using a normal distribution. A normal distribution is the bell-shaped curve. And then we have confidence.t, returns the confidence interval for a population mean using the student's t distribution. This is what is used in science. We use the student's t distribution. And so we're going to use this one here. So confidence.t, I'm going to use that function, and then I plug in alpha. Alpha is the decimal of what's outside. So if I want 5% outside, it's 0.05 out of 1, and so that's my alpha. An alpha of 0.05 means we have a 95% confidence interval because it's 0.95. And so 0.05 outside. Comma, and then I'll put in my standard deviation, which was calculated in the previous cell, which is B10 in this case. And then I'll put in the sample size. And so I need to count how much data I have. 1, 2, 3, 4, 5, 6. 6 data points. So I'll type in 6 here for the size of my sample. Now, what happens here is, due to the mathematics of this, the wider the standard deviation, the wider the confidence interval, the less confidence you can have in it. Okay, that's one. The other thing is, the bigger the population, the narrower the confidence interval. The smaller the population, the wider the confidence interval. And so I'll type this in, and I get 0.79. So to capture 95% of the data, I need to widen it out a little bit to 0.79. And so what we do in science is we report it like this. We report it as 10 point, I think we had 2 decimal places. So I'm going to average this at 10.78. Okay, and then what we do is we insert the plus minus symbol here. And we're going to put in our confidence interval, 0.79 in this case. So 10.78 plus or minus 0.79 will be our pH reading here based on this. And let me format this. So now, we're going to just repeat the same calculation over here. Here, we have a much narrower distribution of data. And so here, our confidence interval will be our average will be 10.78 plus or minus point 0.0009. So this is the tale of 2 averages. One average had a wide spread of data, ours, and another average had a tight spread of data, hypothetical, imaginary data here. And you can see that which average can you have much more confidence in? This average we're going to have much more confidence in here because it has much tighter spread. So what this says is that we have 95% confidence that the true average, the true value, lies within this range here. Whereas in this one, we're a little bit uncertain. You know, we got to have a wider range. So the pH can range anywhere from 10.01 to 11.5 or 6, 5.57. Yeah, 11.57. So 10.01 to 11.57. And this one is going to range from like 10.77, 9, 1 to 10.7809. Is that 3? Yeah. Now, if I had less data, let's say if I eliminate some of the data, then it's going to even broaden it. And so it turns out when we look at the student's t distribution, you know, the more data, the better, but it's diminishing returns. And so let's look at the student's t distribution here. Let's hope this one is good. I'll just copy this off the website here. Students' T tables are very common. Maybe I can't copy it off the table there. No. Let's see if this one is. Just give me one table that just show me the table. Okay, maybe this one is okay. Well, this one's good enough. Okay. Just look, this is 95% confidence interval for a student's T distribution, 0.05 with an alpha. And then what we see is these are these multiplication factors. So this is what we multiply the standard deviation by. So if we only took one data point, this is actually one tail. We'd have to double this. It'd be 12.6 would be the number. We have two types of tables for this. The two types of tables are looking at one side or both sides of the bell. This is kind of bell-shaped curve. So if we look at both sides, we need to double this number. So this first one's 12.6. So if we only took one data point, then we have to multiply our standard deviation by 12.6 in order to compensate for just having one data point. If we take two data points, it's much better because then it's about 6 we multiply the standard deviation by. If we take 3 data points, then it's about 4.6, 4.7 that we multiply it. And so it's getting better and better. The more data points we take, the better it gets. And so going from one data point to 3 data points is a huge change in our confidence because we start off at 12 and then we go down to 4. But if you look at these points, it kind of flattens out. Do you see? It stays around the same value. And so it turns out that most experiments require a minimum of 3 trials. They require a minimum of 3 trials to get a statistically meaningful result here. And we could do more, but as far as the best trade-off between time, that is to do the experiment, versus number, 3 is it. And so we get the maximum benefit from doing this. But more is better if it doesn't take too much time, but it's not hugely better. And so if you look at the table, obviously infinite's best. If we go infinite, and some of these tables will show you going out to infinity, but San Jose State, they must have a decent table here. Yes, they do. Full of a bunch of ads. So if we go out to 1,000, let's say, then it just dropped, from, okay, it just drops to 1.6, versus if we took 3, it's 2.3. And so the cost increases and the benefit's not so great. The greatest benefit comes in the first 3 here. All right, so that's what we're going to do. That's what we should do for these. But what we're going to do for our lab report is not this. What we're going to do for our lab report is this. Now that we have our pH is 10.78, we don't have the most confidence in that because it's kind of spread out between 10.01 and 11.57. But what we're going to do is we're going to do a calculation here. And the calculation is we're going to determine the experimental Ka value and Kb values. So I'll pick the hard one for the first one, kind of a hard one. And so what we have is we have a pH of this, which is 10.78, which is a base or an acid. This is a base, and it's a pretty decent base. 10.78 is kind of a high pH, so it's a decent base. Do you know what the molarity was? This a 0.1 molar sodium carbonate solution? Yeah. Okay. And so if it's a base, then do bases produce hydronium or do bases produce hydroxide? Bases produce hydroxide. So the pOH is equal to 14.00 minus the pH. And so therefore the pOH is going to be 3.22. And therefore the hydroxide ion concentration is going to be 10 to the minus pOH, which is equal to 10 to the minus 3.22 molar. And so I want to plug that in here. Into the calculator. .22 negative gives me a hydroxide ion concentration of 0.000006. All right, now how many sig figs do I have here? In the power function, everything after the decimal is significant, so I have 2 sig figs here. And so I'm only allowed 2 sig figs here, so it's 60, but I'm going to carry extra, maybe 2 extra, 2.5 molar. Now this hydroxide is the equilibrium hydroxide. And so the equilibrium hydroxide is what we call the total hydroxide. Now the unfortunate thing is we picked a hard one to begin with because carbonate is what we call a dibasic base. And so carbonate starts off with plucking 1 proton off water to form bicarbonate and hydroxide. This we call KB1. And then bicarbonate can pluck a proton off water to form carbonic acid and hydroxide. This we call KB2. And then finally, water can also contribute hydroxides. Which will be KW. So to make our life a little bit simpler, we're going to make an assumption here. We're going to assume that the bulk of the hydroxide comes from step 1. And we're going to assume that there's going to be a negligible contribution of hydroxide from step 2 and step 3. We're going to assume that nearly all hydroxide produced in step 1 and so we're going to determine KB1. Is this assumption good? Yeah, a lot of times it's quite good for weak species, like weak polyprotic acids For example, we saw yesterday with phosphoric acid, it was pretty good. The hydronium came from step 1, and for weak polybasic bases. For strong ones like sulfuric acid is a special case. We can't make this assumption. And so what we're going to do is we're going to fill in the ice table as much as we can. And so the carbonate concentration will take as 0.100 molar. That's the initial carbonate concentration. And what we're going to assume is nothing has happened at the beginning. And then the carbonate's going to produce hydroxide, and it's going to produce 0.000006025. So at the end of this, we're going to assume we're going to have 0.000625 molar hydroxide here. And then what we need to do is we need to get the rest of the data in here. And so the rest of the data is going to look like this. Looks like it froze. It froze here. Okay, tell me what this is here. This is going to be minus x. This is going to be plus x. This is going to be plus x here. And then we're over here, we're going to have 0.100 minus x and then x. Normally we use k to solve what x is, but in this case we can't use k. But can you tell what x is? Yeah, what is x? Yeah, 0.000625 molar. This is our x. So this hung up here. Let me switch back to Word. And let me get the data for Excel. So the carbonate is going to be 0.100 minus 0.0006025. Is that correct? This is for the carbonate. And that's going to give us 0.0993075 molar. And then water, we ignore that. And then this is going to give us bicarbonate, which is going to be 0.0006025, and hydroxide, which is also 0.0006025. So we can calculate our Kb value now. The Kb value is going to be the bicarbonate concentration times the hydroxide concentration divided by the carbonate concentration. Oops. Didn't mean to do that. And so what does that come out to? I'm just going to punch in the numbers here. So this, I'm just going to square that divided by 0.0993075. And so I get a Kb value that is going to be 3.65 times 10 to the minus 6. This is the Kb value for carbonate. All right. What is the accepted Kb value? The data like in our chart in our room, in our classroom is kind of old. The data there. I want like the most current data. Where can I find the most current data? Our textbook, but our textbook's fairly new, but did they update all the data in there? Maybe they're just using the old data from previous editions. How can you be sure that they're using the latest data? In fact, where can I find the latest Ka and Kb values? Do you think maybe Wikipedia has that? Or is Wikipedia updated continuously? On some cases, yes, you could find the latest data, but how can you be guaranteed that they took the latest data off Wikipedia? Do you know that? We have no guarantee, so where can we get the latest data guaranteed? Kind of. The latest, when I say latest, I mean latest that's been reviewed. The latest, that you could have the latest data which somebody just came up with, but it hasn't gone through a review process. And so the latest data, you have to pay for it. And do you know where you can find it? There's a couple of books. Nowadays they don't use books as much, but they're still being published, these books. They publish them every year. And their job is to keep you informed of the latest data. Does anybody remember those books, the names of the two books? Mentioning Chem 1A, Chem 4 too. No? One has a weird acronym. We would probably look at the one is the CRC. Does that ring a bell? What do you remember what CRC stood for? This is the name of the publisher. You might think it's odd, but this stands for the Chemical and Rubber Company. But they have a book. It's not called Chemical and Rubber Company book. It's called the CRC Handbook of Chemistry and Physics. So if you want the latest data, you'd either go online, you have to pay for it, or you just buy the latest edition of their book, and they update it annually. It's their job to update it annually. I don't. I have a copy of the CRC, but it's from the 1980s. You can buy old copies cheap, because everybody wants the newest edition. But when I bought it, it was still like really expensive. I think it was like $300 or something. It's a very thick book. Another source of data that's updated annually is the Merck Index. And so these two are data sources that are up to date. We don't have the budget for this, subscriptions for these, so we don't subscribe to it. So we just use old data. So the data we're going to use is from our book, and our book we don't know. Did they really update it or did they not? But if it's important for you to know, then you need to get the latest data. And so we're just going to figure out what is the Ka for bicarbonate in our book, and then see what it comes out to. So there are Ka tables. Actually, there are Ka tables all over the internet, but we don't know when those were published and how reliable that data is. But for our work, it's not so crucial. I mean, we have quite a big degree of uncertainty there already. And so Ka for bicarbonate. Bicarbonate's really important in biochemistry. So this is, I think, off Wikipedia, probably 4.7 times 10 to the minus 11. But there's probably more. 4.7 times 10 to the minus 11. University of Washington has a table of acid and base strength. It's good. This says 4.8 times 10 to the minus 11 from Chegg. This is 4.7 times 10 to the 11 minus 11 from Chegg also. This is from, I think, Chang's textbook. 4.2. Can't be right. 4.2 times 10 minus 7. I think I'm misreading that. And so we could do a quick review and see. 4.8 times 10 minus 11 off Brainly. So which should you use, 4.8 or 4.7? Well, we'd look up in the CRC. CRC is probably the latest for the reviewed. But we're just going to use the AI version here. 4.7 times 10 minus 11. So this is going to be 1.0 times 10 to the negative 14 divided by 4.7 times 10 to the negative 11. So 1 times 10 to the negative 14 divided by 4.7 times 10 to the negative 11. Oops. Screwed that up. I wonder if I could edit it. Yeah, I can. Okay, now it worked. 2.12 times 10 to the negative 4. So what did we just calculate? We calculated 3.65 times 10 to the negative 6. Kind of a huge error. Isn't that? I think. We should have gotten a much higher pH. But I don't know what the concentration was. All right, so we're going to do this, and we're going to compare, our experimental value with the accepted value. And that's what's going to be the report for this, just some calculations. Most of the species are monoprotic, monobasic, so it'll be easier. This is the carbonate, was the dibasic one. We'll look at these numbers later. We got the numbers, then next comes analysis. Why are we so far off? Okay. All right, so what we're going to do today is we're going to repeat the pH titration, but when we repeat the pH titration, you don't have to do the trial titration. What you need to do is you need to look at your titration curve. And what you're going to want to do is you're going to want to use the exact same amount, or as close to it as possible, that you use for your other titration. And then you got to make sure you catch the waves. So look at your data from your last trial, and then what you're going to do is you're going to tighten up the interval where it starts to rise. And so you should have a good idea of where it's going to rise based on your previous titration. So it should go much faster this time. Your calibration, you're going to have to recalibrate it every time. In fact, sometimes you recalibrate it during the day if it starts to drift, the pH meters. Yes. But you'll have to recalibrate the pH meters again today. So go ahead and check out the equipment and get started with this.